Hey everyone, in this video I will do an inferencing with this model Yarn Llama 2 13B128K. So this is a state-of-the-art language model for long context, that is 128K is a context window length, and this model was further pre-trained on long context data for 600 steps. And note that this model requires flash attention library in order to function correctly. And so they have given the exact commands that you have to run to get your flash attention installed properly. And also, as per this model card from Hugging Face, there is no specific prompt format as this is a pre-trained base model. So let's start with the VS Code. Alright, I'm in this notebook that was given by the developers of this model themselves as an example code to test the inferencing capability of this model. So as a first thing, so I'm only making a very small cosmetic changes into the notebook. It pretty much I'm using it pretty much the way that was given by the developers. So the first step is to install these flash attention, and this was instructed in the model card of their Hugging Face page. This particular comment here, we can see that subdirectory and CSRC rotary, these two things have been added to the comment, and this means that the installation should be done from the rotary subdirectory within the CSRC directory of the cloned repository. This approach is used for installing packages that are not directly available on PyPy or when a specific version of a repository is required. And beyond that, I need the regular modules from Transformer, so auto model, causal LM, auto tokenizer, etc. And then this part. So here the plan is that this model is 128K context window, which is a very long context window, and we are going to test the inferencing capability of this model by providing a very long text. So this particular book, The Adventures of Sherlock Holmes, the entire text of the book is available. And we have defined a variable complete book, which has the entire text of this very long book. And this is almost like 20,000 words. That means it will be like 28,000 or 30,000 tokens. And so the model will read the entire book, and then we will ask questions based on this particular book. That's the plan here. And next, our model path, which is the name of this particular model, which is coming from No Research Yarn Llama 2 13B128K, defining the tokenizer. And then I need to get the book token length, which is coming from by applying the tokenizer on the complete book and then taking the len of the tokenized book. And yeah, of course, you have to get it from the input IDs and taking the 0th element. And config is coming from llama config, and model is our llama is coming from llama for causal LM from pretrained, and then you pass the model path, which has been defined here. And the next part is all important part, which is preparing the KV cache for book prompts. And so for that, I have these little pre-processing first. So I'm just formatting kind of the instruction for the model. So book prompt is initialized with an empty string, and then I'm adding this statement: you are given this novel, and multiple choice quiz at the end. Please read and understand the novel carefully. Then I'm passing 2 line breaks with a start, and then passing the entire complete book. Remember, this complete book variable has our entire 25,000 words or so book that is of importance here. And after the complete book, I am also passing the end after 2 line breaks. And then here is an answer sheet for the multiple choice question quiz about the novel, The Adventure of Sherlock Holmes. So based on your understanding of the novel above, please answer the following multiple choice questions as accurately as possible. Okay. And then another thing, I am passing these add BOS token, which stands for beginning of statement. Let's quickly understand this particular thing here. So this add BOS token, this parameter comes from transformers.llama tokenizer class in Hugging Face transformer library. And this is to control whether or not to add a BOS token at the start of sequence. Now, what is the meaning of add BOS token set to true? So add BOS token equal to true setting in the tokenizer is used to prepend a beginning of sequence, that is BOS token, to the input text. This is particularly relevant for models that are trained to expect a BOS token at the start of each input. The BOS token serves as an explicit signal to the model indicating the start of a new sequence. So a BOS token can be crucial for establishing the context at the very beginning. It helps in initializing the model's internal state appropriately, especially when generating responses or processing input text in a way that's consistent with its training. And in fine-tuning scenarios or when dealing with a custom prompt structure as seen in this code, ensuring that the input format closely matches the format encountered during training of the model can significantly impact the performance and accuracy of the model. Hence, the use of add BOS token equal to true aligns the input format with the model's training regime. And now the most important part of this entire notebook, which is to generate and define a global variable named book KV cache, which represent the entire book's key value cache. And to generate that, what we do is we take the model that has been defined earlier and then pass the entire book encoding. Remember, our entire book encoding is defined here, which is we applied the tokenizer on the entire book prompt. And what is book prompt? It has a complete book inside. Before that, it has these starting tokens. You are given this novel, and also it ends with this instruction here, the answer sheet, etc., etc. So practically, this book encoding has the entire book within it, and from that we prepare this book KV cache. And the main way to create that is this particular parameter use cache equal to true. Let's understand this quickly. So use cache equal to true instructs a model to utilize and update an internal cache of key value pairs derived from the self-attention mechanism. If use cache is set to true, then past key values are returned and can be used to speed up decoding. Now here in this particular line, you don't see the past key value parameter, but we will see in a second that again it is used within this method ingest prompt. I will discuss about this in a second. And there I'm using past key values, and that value has this book KV cache, which is coming from the global variable we are defining right here. Now in transformer architecture, each layer self-attention mechanism computes the key and value pairs based on the input tokens. These pairs are vital for determining how much token in a sequence relates to every other token, influencing the final output generated after processing the sequence. When processing sequences incrementally, as in this case where tokens are fed one by one, retaining the context from previous tokens is very, very essential. And that's where by setting use cache equal to true enables a model to store and reuse the key value pairs from previous tokens. This caching mechanism is particularly important for maintaining the contextual continuity required for coherent and context-aware outputs. Without use cache equal to true, the model would just treat each token in isolation, losing the accumulated context and significantly degrading the quality of the generation or prediction task, especially in long sequences. So basically, in summary, what this use cache true is doing, it's a directive that optimizes the model's ability to handle sequential token processing by preserving and leveraging the contextual information from the self-attention mechanism across the sequence. This leads to a more efficient and contextually coherent outcomes in a language modeling task. Let's understand this with a quick example. Let's say you have M input tokens and you want to generate N output tokens. So without cache, the model computes the M hidden states for the input, then generates a first output token. Then it computes a hidden state for the first generated token and generates a second one. Then it computes a hidden state for the first two generated tokens to generate the third one, and so on and so forth. However, since the output side is autoregressive an output token hidden state remains the same once computed for every further generation step. So recomputing it every time you want to generate a new token seems wasteful. With the cache, the model saves the hidden state once it has been computed and only computes the one for the most recently generated output token at each time step, reusing the saved ones for hidden tokens. Now, I said that this caching optimization mechanism is applicable only for autoregressive models. And what do I mean by that? So in autoregressive language models, each token's generation depends on the previously generated tokens. For instance, when generating a sentence, a model produces one word at a time, and each subsequent word is predicted based on the previously generated words. When a token is generated during this process, its corresponding hidden state, which is a representation capturing the contextual information up to that point, is computed. In an autoregressive setting, once this hidden state is computed for a generated token, it does not change in further generation steps because the previously generated sequences or context remains constant. This constancy allows for an optimization, which is what we saw with caching. So with caching, instead of recomputing the hidden states for all previously generated tokens every time a new token is added, which would be computationally intensive, the model can cache these states. When generating the next token, the model reuses these cached states and only computes the hidden state for the new token. So in simpler terms, for a generated sequence like token 1, token 2, token n, once token n is generated and its hidden state is computed, this state will remain the same for the generation of token n plus 1, token n plus 2, and so on. The model thus does not need to recompute it each time, which saves on computational resources and time, especially for longer sequences. And this caching mechanism is what makes autoregressive model efficient for generation tasks. It's a form of dynamic programming where previously computed results, that is, the hidden states, are reused, avoiding redundant computation. However, remember that keeping use cache equal to true does increase the GPU VRAM usage. This increased usage arises from the need to store additional data, the key and value pairs from the self-attention layers in memory. So when use cache equal to true is set, these pairs are saved in GPU memory for each token processed. This caching allows a model to reference previously computed attention information, which is crucial for maintaining context in sequential processing. However, the trade-off for increased VRAM usage is improved performance in generating coherent and contextually accurate outputs. So the point is that to use cache in this way, you need to have more VRAM in your machine. All right, now coming back to the original notebook. So here the next method, generate multiple choices. This is just a formatting function. So what I'm doing, I'm passing a question, then adding a new line for the 4 different options, because the whole idea is to give a question and then give 4 different options, and the model will give the correct answer. So it is just doing that. That is formatting my question, and ultimately returning from the method is this prompt question. And then there is another method, all important ingest prompt. So this method is basically ingesting a prompt and updating the global book KV cache that is we defined earlier, this variable here. So the important thing to remember here is these Python fundamentals. That is, I am defining this book KV cache inside the ingest prompt with this global keyword. So the global keyword in Python is used within a function to refer to a variable that is defined in the global scope outside of the current function. Without global, any variable assignment within a function creates a new local variable that is local to the function, unless that variable is explicitly declared as global. And in this case, what is our global variable? We have already defined it earlier. That is outside the function, which was here with the book KV cache. So the effect of this is that any changes made to book KV cache inside the ingest prompt function will be reflected in the global book KV cache variable. This is crucial here because the function updates a book KV cache with new key value pairs generated by the model for each new token ingested from the prompt. Without the global keyword, these updates would only modify a local copy and would not affect the global KV cache. So, leading to incorrect behavior in subsequent operations that rely on this cache, because we in the subsequent operation we need the global book KV cache, which is updated with the current prompt. That's the whole purpose of doing this global keyword here. So basically, in the context of ingest prompt method here, the global keyword is used to indicate that the reference to book KV cache inside the function should be treated as a reference to the globally defined book KV cache variable, not as a local variable specific to the function. Now, going inside the ingest prompt method, first I'm just encoding this particular prompt from this that is a current prompt and also the ground truth, and separated by a single space. Return tensor is PyTorch. Then I am taking the input IDs and giving and taking the entire thing to the CUDA memory. And now let's see here, ingest question prompt tokens one at a time. So I'm passing these torch.inference mode. So this context manager is used for running the model in inference mode. It optimizes memory usage and computational efficiency by disabling gradient calculation, which is unnecessary for inference. And we did the same thing earlier as well. That is when I did calculated the book KV cache outside. Here also we use torch.inference mode context manager. All right. Now inside here for I in range encoding.shape -1. So this loop iterates over the length of the encoding tensor. The encoding tensor holds the tokenized representation of the input text, and encoding.shape -1 gives a total number of tokens in the sequence. Now the slice operation right here with the 3 dots, this extracts a single token at each iteration. And then I'm passing past key value equal to book KV cache. This argument feeds the previously computed key and value pairs from the transformer self-attention mechanism into the model. It's a mechanism to maintain the context across multiple forward passes that we discussed in detail just now. So this book KV cache is right now coming from our initial global variable book KV cache. That is when this ingest prompt method is executed for the very first time. It will take the first value, that is which includes entire tokenized text as its past key value past key values. So this expression here, that is underscore comma book KV cache equal to this entire right hand side. So basically it means the output of the model call is unpacked into 2 variables. The first variable represented by the underscore is the logits for the current token, which is ignored in this context. And the second variable book KV cache is updated with the new key value pairs generated in this iteration. This update is crucial for maintaining the evolving context as the model processes each token sequentially. So the overall logic of this ingest prompt method that is to iteratively ingest each token of the input prompt into the language model, updating the key value cache at each step. This method allows the model to build up and retain context over the sequence of tokens, which is critical for generating the coherent outcome. And the way you will invoke the ingest prompt method is, this is an example. So I'm passing the question and also all the options and the ground truth. Ground truth in this case is option B, which is the correct answer of this question. Now let's go ahead. So I am having another method here, print predict. This is the method actually I will use again and again to create the question and answer from the model. And the print predict is actually very much the same. Only difference is that in ingest prompt, I use the book value book KV cache as the global value of this variable. But in the In the print predict method, I am using the new KV cache as my previously defined book KV cache. And then otherwise with torch.inference, I'm doing the same kind of extraction of the KV cache and the logits from the model by passing it each prompt. And then I'm getting the actual logits with this expression 0 and -1. And also I need to get the apply the argmax, torch.argmax to get my actual max logit. And the decoded output will be tokenized at .decode max logit.strip. And that's my answer from the model. So what it's doing is that it is printing the answer from the model and also the ground truth, that is the actual true answer of the particular question. And then finally returning from this print predict whether its model predicted correctly. This is a Boolean value that I'm returning. And then I'm invoking this print predict again and again. So we can see that this is the kind of way that this notebook invokes the print predict again and again. And finally, this is the output after invoking that method so many times. So this is my question at the very first sentence. This is my answers, all the options. This is the prediction from the model. Answer is D and ground truth is A. Similarly for next A and D. And we can see that this is actually not matching. So overall, this model got something like 55% of the answer correctly. So overall, this notebook was a simple demonstration of this model. Now, in this particular instance, I did not find the accuracy of this model to be great, but the main point of this model is that that's a huge, large context window. The 128K context length opens up endless possibilities for documents AI, where it can be used for understanding and processing longer and more complex documents effortlessly. And the commercial license of this model also makes it accessible for various industries and applications, alongside with the capability to handle extensive context. And the magic mainly behind these very large context lies in the cutting-edge yarn scaling technique, which pushes the boundaries of the context length while maintains top-notch performance. The models have similar performance to the Llama 2 base model on the Open LLM benchmarks while scaling context length directly to 128K. But remember, to use the full context length of this model, you need really large VRAM of your GPU. So of course, no consumer GPU will support it very much. Alright, that pretty much wraps up this video. Thank you very much for watching. See you in the next one.